share screen now, or?
Sure. I'll anyway trim the initial portions before posting it online.
Okay.
So that it starts right.
Share screen now, or?
Yeah, we can see the screen.
Okay, good.
Do you want to make it full screen and check if?
Sure. Yeah. Is it okay now?
Yeah.
Right. I can start whenever you want me to.
Yeah, I think, let me just start. So yeah, welcome everyone to the last talk of the season for the Foundations of Data Science Virtual Talk Series. So we are very lucky to have Hamid Hassani here today. So Hamid is an assistant professor in the Department of Electrical and Systems Engineering, and as well as the Computer and Information Sciences Department at University of Pennsylvania. So prior to that, he was a research fellow at Simons Institute at UC Berkeley, affiliated with the Foundations of Machine Learning program, and also a postdoctoral researcher at the Institute of Machine Learning at ETH Zurich. So he had received his PhD from EPFL, and he had also received the IEEE Information Theory Society Dissertation Award for his PhD. He's also a recipient of many other prestigious awards, just to mention a few. He obtained the 2020 AFOSR Young Investigator Award, the 2020 Career Award, and also the 2020 Intel Rising Star Award. So today he will be talking about how geometry of perturbations play a role in robust learning. Right.
Okay. All right. Thanks, Venkata, and thanks everyone for attending the talk. Also, special thanks to the organizers for inviting me. So the talk will be about learning robust models, and a good starting point would be to talk about some of the main applications where robust models are important for. And these are safety critical applications. Here by safety critical, I mean any application where the detections, decisions, and recommendations associated to those applications would impact the well-being of humans. A canonical example would be self-driving cars, where detecting, let's say, pedestrians in a sidewalk would dramatically impact the safety of those pedestrians. There are, of course, many other applications and domains, such as robotics and medical imaging, where the interaction between humans and, let's say, robots, or let's say, learning-based medical detection systems are subject to obvious safety constraints. So the main message here is that machine learning systems, when deployed in safety critical applications, must be robust and trustworthy. And let me now say a few words about this term robustness here and explain how we can mathematically think about it. So when talking about robustness, a natural starting point would be to talk about the phenomenon of adversarial examples. This phenomenon was discovered a few years back. However, it's now grown to its own field within the area of machine learning. And it can be explained using the following simple setup. So assume that you train a standard model using some standard data set, for example, CIFAR, ImageNet, MNIST, and so on. All right, so sorry, there's a chat box. Okay, good. So you train a standard model using some standard data set. Now at test time, when you want to test your model, and this model could be, for example, a neural net-based classifier, anything that you want to think of. Now at test time, when you test your model on newly unseen images or data points, you know that if your image comes from the same domain as your training data points, for example, if this is an image for which some relevant images or relevant objects have already been seen during training time, then you know that your model would succeed with high probability and high confidence in classifying that image or that data points. For example, in this case, your model would be classified, your image would be classified as a panda. And this is no surprise right now, given the success of deep learning and supervised learning. Now, adversarial examples can be explained as follows. Let's take the same image and assume that we add to it a very small amount of noise. The choice of the noise can be made in a way that the following happens. First of all, the perturbed version of the image is imperceptible or indistinguishable with respect to the original image to us as humans. And second, the noise can be chosen in a way that the perturbed image is misclassified by the model that you are using. Okay, of course, the choice of the noise here should be adversarial. It has to be well crafted with respect to the model that we are using, as well as the data point. However, what's important here is that we can oftentimes add a small amount of noise to our images and cause misclassification using the model that we are using. Let's dig a bit more into this phenomenon of adversarial examples and explain how we can geometrically think about it. So in machine learning, typically we treat data points as points inside some Euclidean space, RD, where D could be, or D or the dimension could be as large as the number of pixels inside the image. Now, within each data point, assume that we draw a ball of radius epsilon. Think about epsilon to be a very, very small number. Within this ball, we are looking for perturbation, for perturbed versions of the original image, such that the perturbed version would be classified incorrectly by the model that we are using. And the perturbed version is called an adversarial example. Of course, to find this adversarial example, we need to search through this ball and find the worst case perturbation or worst case adversarial example that can be misclassified by the model. So the choice of this noise is adversarial. However, what's important here is that adding a small amount of noise can cause misclassification. And in other words, our modern learning systems or deep learning systems are highly fragile with respect to these non-bounded perturbations. And this phenomenon is now well documented within the area of machine learning. There are by now thousands of papers that consider different properties of adversarial examples, or also devise different algorithmic procedures to make our models robust against these examples. But most of these papers that have been written so far have focused on two main geometries for the perturbation set. So the most common geometry that I'm sure many of you are aware of is the L2 ball or the L2 geometry. So around each data point X, you draw a L2 ball of radius epsilon. Within this ball, you are looking for your adversarial example. So in other words, your perturbation set is this ball of radius epsilon, the Euclidean ball. There is also another geometry that researchers have focused quite a lot on, and this is the infinity ball of radius epsilon. Or more generally, we can say that LP balls with p bigger than 1 have been studied quite a lot in the community of machine learning as the perturbation sets. Now let's consider a slightly more complex geometry, which is also relevant to these type of balls. And this is the so-called L0 ball, or the so-called sparse attacks. What are the sparse attacks? So sparse attacks or L0 attacks can be explained as follows. So let's take an input data point, think of it as a vector in d dimensions. And the perturbation can be characterized as follows. You would, among the entries of this vector, you want to choose k entries, and the choice of these k entries is up to you as the adversary. And once you choose these k entries, you can change the value of those entries arbitrarily, right? So, and typically we assume that the value k, the number of entries that you can pick, so that the value, so that you can change those values, the number of these entries is much smaller than the dimension of the input, and hence these are you would only change your input at a sparse number of coordinates. Okay, so these are called sparse perturbations. So this is an example, the so-called adversarial patches. You only change your image, your input at a small number of pixels, and it's known that these type of adversarial patches would also lead to huge misclassifications in our modern learning-based systems. Another example is when you have a text that has, let's say, many words in it, and you want to change only a very small number of words within the text in order to fool some classifier. So that's another example of these kind of sparse attacks. Now, the geometry of sparse attacks corresponds to this L0 ball. So L0 ball goes over all the possible k entries, subsets of k entries, and within each of these subsets tries to basically change the so it is unbounded within each of these subsets. It tries to change the value basically unboundedly. So L0 ball, in contrast with LP balls that we talked about in the previous slide when P is larger than 1, they have a much more complex geometry. So they are non-convex, non-smooth, they're unbounded. Essentially, when you decide to change a pixel, when the adversary decides to change a pixel, the adversary could put essentially any value on that pixel, right? That's why they are unbounded. Because of this complex geometry, it can be shown that typically even changing one pixel can fool the classifier. And more formally, there are theoretical results showing that linear classifier as well as feed-forward neural nets can completely fail in this settings, in the setting of L0. And we'll talk about that in more detail later on when we reach to this part of the talk, the corresponding part of the talk. So our traditional classifiers, like linear classifiers or neural nets, basically fail in this setting. So the main message here is that for the L0 setting, for the L0 perturbation sets, we need to really rethink our architecture design as well as learning procedure based on this L0 geometry of the problem. So that was the second geometry that we considered. And so the next natural question here would be, what other types of perturbations or geometries can cause misclassification? It turns out that there are quite a few of those geometries or perturbations. So in addition to norm-bounded perturbations and sparse attacks that we talked about, we can, for example, talk about spatial transformations, for example, rotating or rescaling our data points or images. Out of distribution inputs, it even turns out that the quality and type of the data acquisition device matters. So if you capture your images at training time with one camera, and then at test time, you capture your images with a different camera with different type and quality, then this shift in the quality of the data acquisition device can cause misclassification according to this study that was done a few years back. And finally, there is a very broad class of transformations, which we call natural variation. And these kind of perturbations are caused when we work in natural or dynamic environments. And since the last part of the talk will be about this class, I'd like to say a few words about this class here. So the central question that I'm going to answer in this slide is, how does data vary in natural environments? In order to illustrate the answer, I'm going to consider a very simple and standard data set. So these are data set. This is a data set of images of different scenes captured, I think, in the city of Atlanta. All these images have a street sign in them. And what's important to remember is that all these images are taken during daytime and in a sunny weather. Okay, so that's our condition during training time. And we have like 10,000 images of this kind for different scenes. And the learning task would be to classify the street sign which is inside the image. Okay, so that's a very standard machine learning task. You can essentially train a neural net based classifier for this task. Now, assume that you train your neural net using this data set, and you want to deploy your neural net in real world, meaning that let's say you have a self-driving car, you use this neural net to classify the images that are captured when this car is driving around the city. And so you're using this neural net to basically classify these, the street sign inside these images that are captured. Now, when working in natural environments, the nature doesn't typically give us exactly the same conditions as training time. In other words, the nature could add different types and levels of natural variation to our images. For example, the nature could add a snow to the same scene. Now, the picture on the right and the picture on the left, they somehow correspond to each other. They are about exactly the same scene. They have the exact same street sign in them. So they are semantically the same. However, they differ in the type of natural variation. One is taken in a snowy day, the other one is taken in a sunny day. In the same manner, the nature could add, for example, rain to our images. Or we can talk about a very broad class of transformations here: dirty camera lenses, darkness, fog, blurriness, grayscale, exposure, and so on and so forth. So that gives us a very broad class. And the question that we want to answer here is whether or not our modern deep learning systems are also fragile with respect to these kind of transformations. In order to answer this question, I have provided some experimental results here. So let's take the same data set as in the previous slide. Remember, all the training data points were captured during daytime and in a sunny weather. That's how we trained, that's how our data was, and that's the training data for our neural net. We trained a neural net, and at test time, we tested on images that have different types of natural variation in them. In this case, we test on images that have different levels of snow in them. Now, the curve at the top, the highest accuracy curve, corresponds to images that are test images that are taken during daytime and in sunny weather. So exactly the same conditions at training time. And you see that you get a high accuracy curve because the conditions have been the same. And this is really no surprise because deep learning is successful when there is no shift. Now let's add a bit of natural variation to our images, a bit of a snow here. And you see that there is a small performance drop. If you add more and more snow to your images, you see that there would be a huge performance drop by around 30% or so. So long story short, our modern learning-based systems are also fragile with respect to these kind of transformations or perturbations. And arguably, these kind of perturbations are as important, if not more important, than adversarial examples for our safety-critical applications. So in other words, so the same amount of effort that's been put in studying adversarial examples should also be invested in studying these kind of perturbations. And so what's the geometry of these perturbations? So geometry of these perturbations is quite complicated, right? So if you have different, if you have the same scene under different levels of natural variation, for example, the snow, the geometry is supposedly a complex manifold. Okay, so that's one challenge. The geometry is quite complex. The second challenge is that we don't even know what this geometry is. It's unknown to us because we don't have any analytical model that basically describes for us a snow. And this also comes in contrast with respect to LP walls, where the geometry was known. Sometimes it's complex, but we actually do know the geometry. Here, and we don't even know the geometry. Okay, so that's the third example of the geometry that we have. So, all right. So in this talk, so the talk will have three parts, and I will try to basically, hopefully, cover all these three geometries. The first part will be about L2 perturbations, the simplest possible geometries. Here, the geometry is known, it's simple. There has been a lot of papers and studies on this regarding this geometry. The subject of this part, the first part of this part, would be to talk about fundamental limits of robust learning in the presence of this geometry. And we'll talk about two central problems in machine learning, namely regression and classification, and we'll drive fundamental limits here. The second part will be about the L0 geometry. Here, the geometry is known. We know how to characterize it. However, the geometry is complex, non-convex, non-smooth, unbounded. And as I mentioned before, we really need to rethink our structure and learning procedures regarding this geometry. And second part of the talk will be about new techniques regarding this geometry. And we see that by using these new techniques, we can get guarantees on robustness of the classifiers that we train. And finally, the last part, geometry is unknown, it's also complex. So question is, how do we design robust algorithms? And in the last part, we basically introduce a framework to answer these questions. And as we will see in the last part of the talk, we will see significant improvements compared to the state of the art for these type of transformations, which we call natural variation. All right, so if there are no questions so far, I'll proceed with the first part of the talk, which is on L2 perturbations, basically. So, I will mostly talk about the problem of regression, and I'll have a slide about classification. Essentially, similar results hold also in the problem of classification. First, the regression part is a joint work with Adel and Mahdi from USC. The classification part is a joint work with Edgar, David, and Alex from Penn. All right, so let's continue developing this mathematical picture that we had on adversarial examples. In order to do so, I'd like to take a step back. Actually, I want to go 50 years back and talk about the good old setting of supervised learning. So nothing in this slide will be adversarial. I just want to talk about supervised learning and introduce the notation. In supervised learning, the data, which consists of the feature vector X and the label Y, comes from a distribution D. And the problem of supervised learning is to find a model that minimizes the expected loss. So here, L would, here and throughout the talk, L would denote our loss function, which basically measures the performance of a model theta in predicting the label of X and compares it with the true label Y. Okay, and in supervised learning, we just want to find a model that minimizes the expected loss. So that's just supervised learning. And of course, typically we don't have access to the actual distribution that generates the data, and we only have n IID data points that are generated IID according to this distribution. So the common practice is to basically relax the expectation over data into an empirical sum, and that would give us the ERM problem. So theta hat would be the solution of the ERM problem, which is basically which basically searches for the model that has the best empirical loss over the training data points that we have. So we know that supervised learning has now been very successful, at least on specific applications like image classification. We know that we have hypothesis classes and theta hats, the classifiers that really work well on test data points that come from the same distribution as the training data. In other words, on non-perturbed data points. So theta hat, the solution of ERM, works well on test data point that comes from exactly the same distribution as training data. However, we know that, and we have observed that the solution of ERM fails badly on adversarial examples. Okay, so that's what we have been talking about so far. Now, in order to improve robustness against adversarial examples, it turns out that we have to solve a different objective. Okay, an objective that somehow encodes the effect of these adversarial examples. So the objective can be explained as follows. Data still comes from the same distribution D. However, at test time, the data will be perturbed, and the perturbation is in a ball of radius epsilon. So if you look at the inner max here, the inner max goes over a ball of radius epsilon. Think of it as an L2 ball of radius epsilon around your input data point X. And the inner max is basically searching for the worst case perturbation that maximizes the loss over this ball. And so in the adversarial setting, we are looking for a model that minimizes the expectation over the data, this worst case loss. And the worst case is around this ball of radius epsilon around each data. So that's the problem that we want to solve. Of course, we don't have the distribution. We have n training data points. So one way to relax this problem is through this robust ERM objective, which basically, similarly to the ERM objective, relaxes the expectation into an empirical sum over all the data points, training data points that we have. Here, delta i's are the perturbations corresponding to data point number I, basically. So theta hat epsilon for us would be the solution of the robust ERM problem. Whenever we have an epsilon, this means that there is an adversary involved. And here, for this part, assume that adversary is L2. Okay, so the ball is the L2. All right, so just a quick recap. In supervised learning, theta hat, which is the solution of the robust, which is the solution of the ERM problem, works very well on benign inputs. However, or on inputs that come from exactly the same distribution as training data. However, it fails badly on adversarial examples. In order to improve robustness, we consider the solution of the robust ERM problem, theta hat epsilon, which works better on adversarial examples. It improves robustness. However, it's been observed in almost all the numerical practical experiments that we have had, and also it's been proven partially that the solution of robust ERM, theta hat epsilon, its performance degrades on benign inputs. In other words, the performance of theta hat epsilon on non-perturbed inputs or on inputs that come from the original distribution of the training data is much worse compared to the performance of the ERM solution. Okay? In other words, there seems to be a trade-off here. And in order to explain this trade-off, here I've plotted a two-dimensional plane. On the x-axis, you have the standard error. On the y-axis, you have the adversarial error. So the solution of ERM lies somewhere here. It's a standard error. Its performance on non-perturbed inputs is good. It has a small standard error. However, it fails badly on adversarial examples, or its adversarial error is high. The solution of robust ERM, theta hat epsilon, lies somewhere here. Its adversarial error is lower. It improves on adversarial examples, so it's more robust. However, its standard error is much worse compared to the solution of the ERM. Okay, so there seems to be a trade-off here. If you want to improve robustness. If you want to decrease your adversarial error, you have to pay a price in terms of the standard error and vice versa. Okay, so there seems to be, this is what people observe. And in order to understand the pros and cons on adversarial training, as well as the properties of adversarial examples, such as this property that I mentioned, there are three key questions that we need to answer. First of all, is there a fundamental trade-off between robustness and accuracy? In other words, someone may come and say the following, that you get these trade-offs because, first of all, you don't know how to optimize, how to solve your problems, or second, you may not have sufficiently many data points. In other words, there might be a model, let's call it whatever, theta optimal, that has the best standard accuracy and the best the best standard error, the lowest standard error, as well as the best adversarial error. And there would be no trade-off. This might be possible. So the first question answers this question. The first question basically tries to consider this scenario. Do we have fundamental trade-offs that hold no matter what the number of data points is, no matter what your optimization algorithm is, no matter how much computation power have or not? Okay, so this is like a fundamental trade. Once we characterize these fundamental trade-offs, the next natural question is how can we algorithmically achieve these fundamental trade-offs? And finally, the third question is what's the effect of other parameters that play a role in this setting, like the size and quality of data, model size, overparameterization, and so on. So we're going to answer these three questions in the context of linear regression, or more precisely Gaussian linear regression.
Hamid, there is a question. If you go back to the previous slide.
Yes.
So it seems like in this two-dimensional plot, there is also a third dimension, which is how much power you're allowing the adversary to have.
Yes, fix epsilon. For each fixed epsilon, you can have this two-dimensional plot, but then there is also, as you mentioned, there is a third dimension, which is the power of the adversary. If the power of adversary is low, you should get smaller trade-offs. If the power of adversary is high, I mean.
So will that be like a smooth curve in terms of epsilon? Like you would have epsilon in there in your results, right?
Yes. So you don't get, we don't, at least in these problems that we have considered, we don't see a phase transition. Okay, so there is like a smooth curve.
Okay, I see. Thanks.
Okay, good. Thanks for the question. All right, so let's try to answer these questions in the context of linear regression. So what's linear regression, or what's linear regression in the Gaussian setting? The model is quite simple. So we assume that your input features, or the input, is generated according to the Gaussian distribution. Here I'm simplifying the setting. I'm assuming that the input is generated according to the Gaussian according to the normal distribution. So all the coordinates of the input are, let's say, IIT. And the label associated to data point X is generated according to an inner product of X and a ground truth model theta 0 plus some additional noise, which is independent of everything else. That's just the setting of linear regression, Gaussian linear regression. And you assume that you have n data points according to this setting. And of course, the goal of linear regression is to estimate this ground truth model theta 0 from these n data samples. And we also add an adversarial dimension to this problem. We assume that each input can be perturbed within a ball of radius epsilon by the adversary. Okay, so that's the adversarial part of the problem. Now, there are a few definitions in order to explain our first main result. So given a choice of parameters, a choice of model for this problem of regression, so let's call it theta. Theta is used to predict the label associated with data point X through this inner product that you see. So the inner product of X and theta would give you Y hat, which is a prediction of the label associated to the input X. And the loss that we consider for this setting is just the quadratic loss, which is just the square of the difference between the true label Y and what's predicted by the model theta. Okay, so that's the quadratic loss. Within this setting, we consider the standard risk and the adversarial risk. The standard risk is just the expected value of the loss over the data that's generated according to the distribution, the original distribution of data D. This is just a typical expected loss. We call it the standard risk. And the adversarial risk is the expected worst case loss, where the worst case is over a ball of radius epsilon around each data point. Okay, it's just is when your adversary is attacking. So we want to understand the trade-off, the fundamental trade-off between the standard risk and the adversary risk. That was our first question. What are the fundamental trade-offs? In order to answer this question, our approach has been the following. So consider all the possible models for this problem, all the possible thetas in RP. Okay, for each model, for each generic theta, model theta for this problem, you can compute the standard risk and the adversarial risk. That would give you a pair in this two-dimensional plane. Put all these achievable pairs, any pair that can be achieved by a model, by any model, put all of them in this plane. That would give you a region. Let's call it the achievable region. Now, in order to understand these fundamental trade-offs, we need to study or characterize the boundary of this region. Okay, this is the so-called Pareto boundary of this region, or the Pareto front of this region. Is the boundary essentially on the bottom left of this region? Okay, so what important property does this boundary point, this Pareto boundary have? So every point on this boundary, which is typically called a Pareto optimal point, has the following property. If you want to decrease the standard accuracy and the adversarial accuracy of this point at the same time, even by a tiny amount, then you would fall outside of the achievable region. In other words, there is no model. So for each Pareto point, there is no model that has at the same time a smaller standard accuracy and a smaller robust accuracy or adversarial accuracy than this point. Okay, so these are really optimal points because there is really no better point or better model than these points. Every other model, every other achievable pair has either a higher adversarial risk or a higher standard risk than the point on the boundary, than the Pareto. So we need to somehow characterize these optimal points, Pareto optimal points for this region. Now, good news here is that for the regression problem, the Pareto boundary, the achievable region is a convex region. So we can use a very well-known trick called the supporting hyperplane trick to find the Pareto boundaries or the Pareto points. Essentially, you look at all the lines in the plane which are tangent to this region, and the tangent point would give us a Pareto optimal. How do we characterize the lines? There would, it's like a simple exercise to see that the Pareto optimal point can be found by solving this objective that you see at the bottom of the page. And so lambda is just a parameter that varies from 0 to plus infinity. And by varying lambda from 0 to plus infinity, you would basically sweep the Pareto boundary of this region. Okay, so for every value of lambda, you would basically obtain one Pareto optimal point of the region. So we need to basically solve this optimization problem, lambda times the standard risk plus the adversarial risk. And the minimizer, the model that minimizes the optimization problem, is a Pareto optimal. Now, for the regression problem, for the Gaussian regression problem, it turns out that you can, this optimization problem has a closed form. Okay, and the derivations are like a couple of pages. I mean, they're not important. What's important here is that you can precisely find the Pareto optimal points for the linear regression problem, and hence you can precisely compute the Pareto boundary or the optimal trade-off curve. Here, I have plotted this optimal trade-off curve for a specific example of a linear regression problem. And as you see here, you get a non-trivial curve, a non-trivial trade-off curve. So this curve that you see here is the fundamental trade-off between the adversarial risk as well and the standard risk. If you work on this curve, you are basically reducing the optimal adversarial risk that you can achieve, but at the same time, you are increasing the standard risk, the best standard risk that you can achieve. Okay, so this non-trivial curve essentially tells you that there is a fundamental conflict or trade-off between adversarial risk and standard risk. So there are trade-offs, and these trade-offs are fundamental, and we cannot really get away with them. These hold for every model that we consider for this problem. Now, once we have these trade-offs, the next natural question is, how can we design algorithms that that achieve these trade-offs? Okay, so that's basically the second question. How can we algorithmically achieve these fundamental trade-offs? Now, in order to design algorithms, we need to, so we have already talked about a possible candidate for the algorithmic procedure, and these were the solutions of the robust ERM problem. Okay, so as the family of algorithms, we consider the solutions of the robust ERM problem. Here, this value of epsilon at training time could be varied between 0 and infinity. Okay, so at training time, you're allowed to use any epsilon that you can. Okay, by varying epsilon from 0 to infinity, you get a family of algorithmic solutions for this problem. And what we want to do is to study the behavior or the trade-off between standard accuracy and between standard error and robust error for this family of algorithmic solutions. Okay, and remember, we are using the quadratic laws. Okay, so a quick recap on the setting. We are talking about Gaussian linear regression. Input is generated according to the Gaussian distribution. Label is the inner product of the input and the ground truth model theta 0 plus some additional independent noise. We have n data points from this setting, and p is the number of parameters. P is the dimension of the input as well as the number of parameters, because we are looking for a model theta whose dimension is exactly the same as the dimension of the input. Okay, and the regime of a study for this problem that we consider is the following regime. We assume that the number of data points would grow large. However, the ratio between the number of data points and the number of parameters is kept fixed. This is typically called the overparameterization ratio. If this ratio is large, this means that your problem is basically you have many more data points than your parameters, and if it's a small, this means that you have more parameters than your data points. Okay, so we study this problem in the limit when the number of data points is large, but this ratio is kept fixed. Now, in this regime, you can precisely characterize the behavior of the solutions of the robust ERM problem. You can precisely compute the limit of the standard risk as well as the adversarial risk. And these formulas that you see here are given in terms of some parameters. These parameters can be found precisely by solving a simple 5-dimensional optimization problem. This optimization problem has a very nice behavior. You can use, the solution is unique. You can use a simple alternating optimization procedure to find the solution of it. The objective is quite complicated, it's given here, but let's forget about the objective. What's important here is that you can solve this 5-dimensional optimization problem to find these parameters and compute the precise values of a standard risk and adversarial risk for the solutions of the robust ERM problem. Okay, so what's the main takeaway here? So the main takeaway here is the following. So you get, for each value of delta, you would get basically a trade-off curve. And remember, delta was the overparameterization parameter. Now, when, so the curve at the bottom that you see, the black curve at the bottom, is the fundamental limit of our problem. We cannot really do better than this curve. Now, what we see is that if you would only get close to this curve if the number of data points is much, much larger than the number of parameters in your problem. Okay. In other words, if the regression problem is highly underparameterized, then you would get close to this fundamental curve. Also, at the same time, if the problem is overparameterized, you see that we get further and further away from the fundamental curve. Okay. In other words, in this setting, and in the setting of the solutions of a robust ERM problem, overparameterization is hurting robustness. Okay, so that's the main message that appears to hold in this setting. Okay, so overparameterization is somehow at odds with robustness, at least in this simple setting of linear regression when we want to solve the robust ERM problem. So that's the second message. Now, this was about regression. For classification, you essentially get very similar results, meaning that there is a fundamental trade-off between standard risk as well as the robust risk. And this trade-off holds for no matter what your model is, no matter whether you are using a linear classifier or a very complex neural net. you always have these trade-offs between the standard and robust risk. If you want to decrease the robust risk, you have to increase the standard risk and vice versa. There is always these trade-offs that are valid no matter what model you are using. So that's about basically the extension of these results to the problem of classification. So that's the end of the first part. I think let me quickly summarize what we learned from this the first part. There are fundamental trade-offs between robustness and accuracy. That's the main message. And in classification, as long as so think about like a mixture of Gaussian. As long as your data points have overlap, as long as the two Gaussians have overlap, you see that there are non-trivial and fundamental trade-offs. And also, we also talked briefly about the effect of overparameterization and saw that overparameterization negatively affects robustness in this setting. Now, there is a line of work that basically shows the effectiveness of using non-parametric models for the problem of robustness. Essentially, what they observe is that, first of all, for some real-world data sets like the CIFAR 10 data set, there are some separation properties between the data points and the classes. And because of these separation properties, they can prove that there exist non-parametric models that, at least for small values of epsilon, that have no trade-offs, meaning that these non-parametric models that have very good robust accuracy as well as very good standard accuracy. So there seems to be like a conflict between these results, right? And the open problem is really this: what's the problem, and why do we see trade-offs in practice? In practice, when we want to solve this problem of robustness on the CIFAR 10 data set, we really cannot. We always see a trade-off. We see a strong trade-offs between robustness and accuracy. Whereas these results show that there are at least non-parametric models that do not suffer from these trade-offs. So is the problem with using neural nets? Is the problem with using the problem is using overparameterization? We don't know. That's an interesting open problem to pursue further. Okay, so that gives me the end of the first part. Let me quickly talk about the second part of the talk, which is on L0 perturbations. And this is a joint work with Mark, Payam, and Ramti. So what was the setting of L0 perturbations or sparse perturbations? Remember, you have your input. You can think of it as a p-dimensional vector, and the adversary can pick k coordinates, whatever k coordinates it wants, and it can change the value of those k coordinates arbitrarily. Okay, so the geometry here is the L0 ball. We call it L0 ball of radius k, but this is like it's not, doesn't have any radius. It's just that you can pick k coordinates, and k is much smaller than the dimension of the input. And remember, the geometry is highly non-convex, non-smooth, and also unbounded. As I mentioned before, in this setting, linear classifiers and feed-forward neural nets fail. You can show that they completely fail in this setting. And also, this setting has recently gained a lot of attention across the ML community, machine learning community, as well as the natural language processing community, because of this example that I told you. You can pick a few words in a text, change those words, and then you can fool the classifier. So this has applications in natural language processing too. So the question that we want to answer is the following. So now we know that, for example, neural nets do not work in this setting, okay? Or linear classifiers also don't work. Question is, what principal components should we add to our classifiers in order to make them robust against these kind of perturbations? So that's the main question that I'm going to talk about in the next few slides. And the way I approach this question is the following. I first consider a very simple model for my data, the Gaussian mixture model. And we will see that there are two important components that have to be added. They are necessary to be added in order to improve robustness. And once we figure out what these two components are, we will try to extend these two components to real-world data and real-world settings and neural nets. And we see that these components are also helping in terms of robustness in improving robustness in real-world settings. So what's our setting here? Let's just start from the simple theoretical model. So here I consider the Gaussian mixture model for generating the data. Okay, so the label is assumed to be generated uniformly at random between -1 and 1. And given your label, your input would be Gaussian conditioned on the label. In other words, if y is +1, then your feature vector would be generated according to a Gaussian with mean plus mu, and let's say variance, covariance matrix, the identity matrix. And if your mean is if your label is -1, your feature vector will be generated according to a Gaussian with mean minus mu. Okay, so that's how the features are dependent on the labels. So that's called the Gaussian mixture model. We know for this model very well that the optimal classifier when there is no adversary is the base optimal classifier, which is a very simple linear classifier given in this form. So y hat is just the sign of the inner product of mu. Mu was the mean vector, mu and the input x. Okay, so this very simple classifier is optimal when there is no adversary. Okay, and in this figure that you see on the right, I just schematically shown this linear classifier. So your input x is inner product, so it goes into an inner product with respect to the vector mu, and the sign of that would give you basically the label, the predicted label y. Now, in the adversarial setting, in the L0 setting, remember the adversary can pick k coordinates and change their values arbitrarily. Okay, so k coordinates here, I mean, as you see on the right, k coordinates can be picked, and it's now easy to see that if you can even change one coordinate arbitrarily, then the linear classifier fails, because you can just pick one of these coordinates for which the weight of the linear classifier is non-zero, and by changing this coordinate appropriately, you can always flip the sign. Okay, so that's the reason why linear classifiers completely fail in this setting. And again, the question that we want to answer is, what can we add? What are the key components to add to this base classifier in order to make it robust against these kind of L0 perturbations? It turns out that there are two key components that we need to add: truncation and filtration. So truncation removes outliers, as I'll discuss, and filtration removes non-robust features from the input. Okay, so let's see what truncation is. Truncation is like a famous idea in the field of robust statistics. Okay, so the basic idea is this. So remember, the base optimal classifier was the sign of the inner product of mu and x. Okay, so this inner product here, which is given as a sum over p values, basically all the element-wise products. Now, truncation does the following. You go over all these p values, and you remove the highest, basically the k top values among these p values, and also you remove the k smallest values among these p values. Okay, these are somehow for us outliers. I mean, it might be the case that the adversary has created these very high or very small values. Okay, so we just remove them. These are our outliers. We just remove them, and we compute the truncated sum, the sum which does not have these outlier values. Okay, so that's the first key component, truncation, and you compute the truncated inner product. It turns out that truncation is not enough by itself to give us the best possible robustness that we can achieve. We also need to do filtration. What is filtration? Filtration is quite a simple idea, and it's quite a natural idea. So there are some features that are highly susceptible to adversarial attacks, meaning that these features in the input vector x, these features, having this feature does more harm than good. In other words, we should just, in the adversarial setting, we just neglect these features. Okay, we just throw them away. We shouldn't use them because these are highly non-robust features. Now, in the setting of Gaussian linear regression, it's fairly easy to get a handle or basically compute or find what these non-robust features are, and we can easily filter them. Okay, so the basic classification algorithm that we will reach to is the following. So you have your input, p-dimensional vector. There are some features that we can compute in the Gaussian mixture model, that these features are non-robust features. Okay, so these features, no matter what their value is, you just have to forget about them. Okay, so you basically remove them or you zero them out. Okay, and then you are left with the set whose the new input, whose sum of coordinates are zeroed out, And then you just compute the truncated inner product with respect to the vector mu. You compute that inner product, you truncate it, and the resulting, the sign of the resulting value would be the predicted labels. Okay, so remember there are two key components: filtration, removing non-robust features, and truncation, which basically removes outliers added by the adversary. Turns out that these two key components are enough for the Gaussian mixture model. So adding these two components asymptotically gives you the optimal robust error that you can expect for this model. Okay. Now, so this was for the Gaussian mixture model. Let's now see how we can extend these ideas to more general neural networks and when we use real world data sets. Okay, so the two key components were truncation as well as filtration. Now, truncation is easy to hard code when you are using a neural net. Essentially, the basic idea is the following. So if you look at for example, the first layer of the neural net, the input, so before you apply the nonlinearity, the input to the neuron would be an inner product between a weight vector and the actual input of the problem, the feature vector x. Now, this inner product can be truncated to avoid outliers added by the adversary. Okay, so truncation is easy to implement and add as a key component, and it can be hard coded into your neural net setting. Filtration is actually very hard to implement because if we want to find non-robust features, we need to have access at least to the distribution of the data. And when we are working with real-world data, we don't really have a distribution of the data, right? So essentially, filtration cannot, in the way that I explained it, cannot be really implemented in the setting. However, we know that adversarial training, we know from prior work, and this is like a general intuition, that when you do adversarial training, you're essentially removing non-robust features. Okay, so adversarial training can be used as a proxy for filtration. Okay, so the second key component can be taken care of by doing adversarial training. What does adversarial training mean? It means that you just basically solve the minimax problem by augmenting the attacked data points into your training procedure by solving the minimax problem, right? This is just the adversarial training. So let's see what happens when you do these two things. So you apply truncation, you hard code it into your neural net, and then you do adversarial training. So we have some preliminary experimental results. Other results are actually being implemented exactly as of exactly right now. So we only have results on the MNIST data set. So here, K is 10. Remember, K was the number of pixels that the adversary can attack. The dimension of every data point in the MNIST data set is around 800. So this means that K is much smaller than the dimension of the input, and these are sparse attacks. Now, let's look at this table at the bottom. You see that on regular neural nets without any truncation that are also adversarially trained, the robust accuracy is around 30% here. And once you add truncation and adversarial training, those key components that we mentioned, so adversarial training is a proxy for filtration, those key components, you see that the robust accuracy was increased to 98% for this MNIST data set. And the standard accuracy is always 99%. There seems to be no trade-off in this setting at this point for this data set. Okay, so this was what I wanted to say about L0 perturbations. I don't know, time-wise, I don't know how we're doing. I can stop here, I can continue for a few minutes, or if there are questions, I'll be happy to answer.
Time-wise, you're doing fine. I think you can go on a few minutes over 3, yeah. So you have about 10 minutes, let's say. And I have a quick question. Like, so when you're doing adversarial training, are you using L0 ball, or are you using a surrogate L1?
Very, very excellent question. Excellent. So L0 ball is highly non-convex. So forget about doing optimization over L0 ball. Very good question. So there are a few tricks that we can use. So one trick that produced these experiments is that you take one of these important attacks, state-of-the-art attacks, for example, this sparse RS attacks, and instead of solving the this attack is actually trying to solve the optimization problem over the L0 ball. This attack that you see, it's a very complicated optimization problem, that's trying to find a worst case point within the L0 ball. Okay, so we use this. I mean, you think of it as one way to solve this very complicated maximization problem over the L0 ball. So we use that in our as our max as a solution to our max procedure in our adversarial training. You can use other things. For example, if you have the L0 ball, I mean, if you are familiar with compressed sensing, what you could do is that you relax the L0 ball to the L1 ball with the hope of being able to find good sparse solutions. That's another way that we are trying to implement right now. But essentially, as I said, the L0 ball is very complex. So if you want to optimize over L0 ball, you have to be a bit creative and find good optimization methods, which are basically which you have no guarantees for.
So would just doing L1 min-max be sufficient, like without truncation, or is truncation?
No. Truncation is necessary. Truncation is necessary. Why? Because even for the linear classifier, changing one pixel can always hurt you. Okay? So in truncation is really a building block that you have to have in this setting. Now, filtration, you can take care of it by doing adversarial training. I think these are equivalent, filtration and adversarial training.
Okay.
Thanks. All right, so let me spend a few minutes, maybe 5 minutes, on the last part of the talk, which is generalization to natural out of distribution inputs or natural variation. Okay, joint work with my student Alex and George at Penn. So, okay, remember nature could add different levels and types of natural variation to your inputs. Okay, and so in this case, we had two challenges. First of all, the geometry is very complex, and second of all, we don't even know the geometry. Okay, so in other words, we don't have an analytical model that basically you give it an image as an input and it adds a snow to that image. We don't have that. Okay, we don't know how the geometry is, and hence the basic procedure that comes to mind, which is very intuitive in this setting, is to first try to learn or approximate this geometry or this model that basically perturbs the data. You learn it approximately, and then you use it in devising robust algorithms for your problem. Okay, so that's the high-level picture. So how do we learn the model? The way we look at this problem of modeling the impact of natural variation is through what we call a model of natural variation. Okay, so think of it as a function, g of x and delta, where x is the input image, delta is a low-dimensional vector, like two-dimensional, three-dimensional. We call it a nuisance parameter. The idea is that by giving x as input and varying the choice of delta, you would get different levels of natural variations added to your original input x, right? So that's the basic idea. That's the role that this nuisance parameter delta is playing. By varying delta, you get images with different levels of natural variation. For example, different levels of snow added to your image. Okay, so this function g, of course, has to be learned. We don't have it. We will explain how you learn it later on from data. But for the moment, assume that you have this function g. You have this model g. Once you have this model g, you can easily figure out, or at least have a handle on the geometry of the perturbations applied on an input x. Okay, so this is what we call the learned image manifold, this b of x. So essentially, once you have this model g, by applying this model g to different values of delta, you can basically sweep over this manifold or this complex geometry of perturbations that are around a point x, an input point x, right? So that's, once you have g gives you geometry. And once you have the geometry, you can use it into this minimax optimization procedure to train and classify. Okay, so that's essentially the optimization problem that we try to solve once you have access to the model g. Okay, so if you look at the inner max in this optimization problem, the inner max is basically going over this manifold, this perturbation set, for which now you have a handle of because you know the model g, and you go over that and you find the worst case perturbation of your input that gives you the maximum loss. Once you have the maximum loss, you feed it to the training procedure of your let's say the weights of your neural net. Okay, so you update the weights of the neural net using this worst case point, and you continue this procedure alternatively until you basically converge or you get to a good model for this problem. Okay, so once you have G, you can just plug it into this minimax optimization procedure to find a good classifier. Now, let me skip these parts. How you solve the inner maxes? I mean, these are fine. There's nothing really new here. How do you learn the model? So the basic idea, as you may have guessed, is to learn the model using data. So in a data-driven manner, right? So we use the recent advances of generative modeling, specifically this very important framework of unsupervised unpaired image-to-image translation networks, to basically learn a model, a function G, that applies these different levels of natural variation to your image. So here, the variation is brightness. You see that by varying your nuisance parameter delta, here at the output, you get different levels of variations applied to your input, which is this image, house number 3 here. Okay, so that's how you learn the model. And let me stop here and maybe just explain one experimental result, which might be interesting to some of you. So here, so the data that we have data from different hospitals. These are, each image is a potentially cancerous cell. And these images are captured from different hospitals. And once you capture images from different hospitals, you have shifts because different hospitals use different devices, they have different environments. So you have shifts in terms of color, brightness, contrast. So images look different. And if you see these images from different hospitals, they are about cells, potentially cancerous cells, but these type of the color might be different, brightness might be different, contrast might be different. So essentially that's the data that you have. And at test time, you might have data points even with different colors and brightness and so on. Okay, so you can apply this framework that I mentioned to learn the natural variation and use it, plug it into this minimax formulation to find robust classifiers. And as you see, this framework that we have advances the state of the art, at least on this data set, by around 20% or so. Okay, so that's the power of learning the geometry first and then plug it into this minimax procedure. We have other results like ImageNet C and so on, which let me actually stop here and for the interest of time and not talk about the other results. All right, thank you very much. Sorry, I think I went over time for a few minutes.
That's fine. Thank you so much. Are there any questions? Like, feel free to unmute yourself and ask. So are there any like list decoding or list learning variants in these adversarial models?
That's really an excellent question. So I haven't seen any. So the only work that I have seen, you can search it. I mean, it's not about this setting. I mean, there is a problem in statistic called robust linear regression, which is a different problem. There, the model is changing. I think there are least decoding results for that problem, as far as I've seen. But about these kind of things, I haven't really seen any least decoding results. So you can basically, for example, produce, you can be creative here, produce several classes and say that the right class is among these, or there are other things.
I was thinking in the terms of like, I give you a list of models and I'll tell you, okay, so there can be like varying trade-offs between
right, exactly.
Scanning risk, and like you can choose one. Right.
Yeah, that might improve. That might like mitigate this trade-off that we see. But yeah, that's a good question.
Are there any other questions?
Yeah, sorry, I have a question for the first part.
Yes.
For the L2. When you define the adversarial risk, will you have the max, exactly, probably was exactly the maximum over this delta? How do you achieve the argmax? How do you get to that?
That's also a very good question. So for the problem of linear regression, that's actually a very good question. So that's an important step that basically eases the derivations and the proof for us. For the problem of linear regression, so when the loss is a quadratic loss, the inner max would be a quadratic function. And when you have the L2 perturbation, you can find a closed form solution for delta.
Okay.
Okay. I mean, it's a very simple exercise.
Yeah.
Okay. You can, in terms of theoretical result, you can explicitly get rid of this inner max because you have a closed form solution and plug in that closed form solution to get like a different loss function. I might have a slide at the end on this. Yeah, here. So this one, you can essentially solve it. And that, forget about these norms. That would essentially give you this closed form solution as your loss.
The results you were showing, they maybe also come from neural networks, deep neural networks. When you were saying that, okay, if you train this way, you lose a lot in terms of standard test error.
Right. So
this was always in linear regression, or it was also like in deep neural network?
This is for linear regression. For classification, okay, so that's another thing. So for classification, what you can show is that for any classifier that you consider, for example, a very complex deep neural network, there is always a linear classifier that has a better standard accuracy and a better robust accuracy. There's always such a that. So you cannot, then this just reduces your analysis to the class of linear classifier, because essentially linear classifiers are the best to study here. That's why I'm saying that forget about very complicated neural network. There is always a linear classifier that's better than a complicated neural network. And then you get this trade-off on linear classifiers. So this trade-off holds for any model. So very good question.
Okay,
thanks.
Hi, I had a question regarding the second part of the talk where you had spoken about truncation and filtration.
Yes.
So for the filtration part, you are looking for all the coordinates of the feature vector, and you're trying to figure out which you are supposed to kick out. Essentially, you are going through a search across the dimension of the feature vector. So in terms of computation complexity, it's pretty high since the feature vector can be...
Yes, exactly. So you're talking about filtration, right?
Yes.
Filtration, the complexity is high. So here, okay, so that's also a very good question. So here, I just want to understand what the optimal robust classifier is, right? I'm not worried about complexity at the moment, okay? So finding the best filtered set, finding the robust features itself is an optimization. You reach to an optimization problem, which its solution gives you the best set, right? And that gives you the optimal filter set. Okay, once you plug that optimal filter set, you get the optimal robust classification performance. Okay, but I agree with you. Finding that filter set in this setting may not be easy, right? But that's a key component. This component is actually necessary for this problem. If you have this component in your problem, if you can afford it, you will reach to a classifier that's optimal. The focus here is to find the optimal classifier and not solving it efficiently. Because later on, we talk about, even in the Gaussian mixture, so if you want to solve it efficiently, you have to do something like adversarial training to take care of filtration.
Okay, thank you.
Did I answer your question, or you still have a question?
Yeah, that's fine. Thank you.
Thank you.
Are there any other questions?